Today we are very happy to have our colleague Dr. Kuo-Chin to come to give this talk about Euclidean traveling salesman problem. He graduated in physics at National Taiwan University, and now he's one of my colleagues doing some complexity study. So let's welcome him.
Okay, thanks for this kindly introduction. So I'm Chen Kuo-Chin, and I'm a researcher in Hon-Hai Quantum Computing Research Center. And it is a pleasure to share our recent work on the exact on the. 我把你的 line 关掉吗？我把你 line 关掉吗？啊，算了，没关系。关好了，因为怕他特殊那个就是，OK， 谢谢。So it's a pleasure to introduce to share our recent work. We design an adaptive algorithm to solve exact Euclidean traveling salesman problem, and we obtain a quadratic speedup compared with the best algorithm up to date. So first, I will introduce the Euclidean traveling salesman problem. After that, I will give an exact algorithm to solve the Euclidean traveling salesman problem. And actually, this algorithm is a divide and conquer algorithm. And our contribution is give an adaptive strategy to divide an instance of ETSP. And finally, I will give some conclusion. Okay, let's start by the introduction. Okay. Let's consider the general traveling salesman problem. Okay, the problem is that we given a weighted graph. A weighted graph is a set of nodes and a set of edges connecting these nodes. Furthermore, there are weights on these edges, and the target of the traveling salesman problem is to find the shortest Hamiltonian cycle. Okay, that is to say we have to find a cycle that visits each point of the given graph with the shortest path. And let's consider a special case of traveling salesman problem, that is TSP in Euclidean space. We are given a set of points, a set of point P in d-dimensional Euclidean space, and the weight of points is actually the Euclidean distance between them. And also, we would like to find the shortest Hamiltonian cycle. Okay, and why we are interested in the special case? Actually, if we could reduce a general traveling salesman problem into the special case, then we could obtain a better time complexity to solve them exactly. Okay, this is the time complexity to solve the general TSP and the complexity to solve the TSP in Euclidean case. Actually, the time complexity to solve an instance in ETSP require sub-exponential time complexity. However, for general case of TSP, we need exponential time complexity to solve them exactly. the first algorithm, the first algorithm to solve TSP, general TSP, is derived by Bellman, Held, and Kopp in 1962. They proposed a dynamic programming algorithm to solve the general TSP with such exponential time complexity. And this time complexity is the best until 2018. And binders cooperate the idea of Bellman and using quantum minimum binding algorithm to design a quantum algorithm that could improve the result from Bellman. So let's now consider the case in Euclidean space. The first sub-exponential algorithm is proposed by Chen. He proposed an algorithm, a divide and conquer algorithm, and often, he considered the case in two-dimensional, and he obtained the time complexity. And a few years later, should I join? Okay. And a few years later, Smith extend the idea of Chen and obtain algorithm to solve a d-dimensional Euclidean traveling salesman problem. And 20 years later, Berg improved the time complexity derived from Smith and obtained the time complexity that is the best up to date. And he also shows that the time complexity is optimal up to the constant in the exponent part of the time complexity. Okay, that is to say there is little room to improve the time complexity. Okay, and our contribution is actually improve the constant in the exponent part of the time complexity. We improve the we reduce the factor in the exponent by a ratio of half, and obtain a quadratic speedup. Okay. Now we are going to discuss the exact algorithm to solve an instance of ETSP. Okay, the exact algorithm is a divide and conquer algorithm. Okay, that is to say we will use the algorithm to split a large problem into multiple smaller subproblems. Okay, and we do the procedure recursively until we could find all of the solution trivially. That is to say, the size of the subproblem should be in the big of constants. Once we can do that, we can obtain all of the solution to this subproblem, and we could merge them recursively until we obtain the solution to the initial problem. Okay, to give the description of the divide and conquer algorithm, we have to discuss 3 topics. Okay, the first is the separator. The separator is actually a d-dimensional hypercube in Euclidean space. Okay, that is to say we could use the separator to partition a set of points P in Euclidean space into 2 parts. One part for those points inside the separator, and the other part for those points outside of the separator. Once we can do that, we should identify the subproblems, one for inside and the other for outside of the separator. Okay, then this is the part of splitting. And finally, if we have the solution to this problem, we could merge them, and we will discuss the merging procedures. Okay. Let's discuss the first part. Okay. The topic of the balance separator is actually to reduce the size of the problems. Okay, that is to say, we would like to reduce we would like to use the separator to split a large amount of points into multiple small pieces. Okay, this is straightforward to define a ratio delta that is smaller than 1, such that we could use this ratio to split the problem. Okay, if we have the problem with size n initially, okay, we use the separator to split it into multiple subproblems with size equal smaller than delta n, and we do it recursively, and the end, the size of problem should be in the big of constants. Okay, once we can do that, we can solve them easily. Okay, and it will indicate that the depth of the recursive steps should be in the big of log n. Okay, and in order to define such a separator, we would like to define a delta balance separator. Okay, this separator could partition a set of points Q into 2 parts, such that each part, the size of each part is smaller than the delta times the size of Q. That means if we have a point of set and a subset of Q, we have a point of set P and a subset of P, we denote it by Q. We could use a separator to divide the point of Q into 2 parts with this relation. And with this separator, we could efficiently reduce the size of the subproblems. Okay, after introduce the separator, we would like to discuss the splitting and merging procedures. Okay, there are three points I would like to focus on. Okay, the first, we would like to define the Euclidean path cover. And this problem is actually could formulate the subproblem of the divide and conquer algorithm. And furthermore, ETSP can be reduced to EPC. Okay, then once we could identify the subproblem in the divide and conquer algorithm, we would like to use the divide and conquer algorithm to find the solution of an instance of EPC. And finally, we would like to improve the time complexity using 2 kinds of separator. And this is our main contribution to improve the time complexity. Okay, let's start by the first part. Okay. It is the Euclidean path cover problem. Okay, the problem is that we are given three sets. There are 3 input. The first input is the set of points P that in D-dimensional Euclidean space, and the second input is a subset of P, and we call them by boundary point, and we denote it by B. And the third input is a perfect matrix M on B. So what is the perfect matrix? Okay, that's given the four boundary points, and we would like to find the perfect matrix. That means we would like to give a pair for each point of the boundary point. So this is an instance of a perfect matrix on B. We could pair these two boundary point and these two boundary points, and these two matrices forms a perfect matrix. Okay, given the three inputs, the target is to find a set of passes that could visit each point of the given input P, such that the endpoint is the perfect matrix. That means if we consider the input of EPC, then we would like to find the red line as the passes. Okay. And furthermore, we would like the passes to have the minimum total length. So this is our formulation on the subproblem of the divide and conquer algorithm. So actually, we could reduce ETSP to EPC, because let's consider an optimal cycle of ETSP. Okay, we could pick an arbitrary point as a point of boundary point, and we copy points at the same position. Then we obtain an instance of EPC. That is to say, we would like to find the path. We would like to find the path that starts from the blue dot and find the path visits at each point of the given graph and return to the origin dot. And obviously, this is the optimal circle in the instance of ETSP. Okay. Sure.
When you separate the points, and at that stage, I mean, so just choosing the locally nearest one.
You mean P and P prime?
No, I mean when you talk about the splitter and separator.
Oh, sorry. Here we have not discussed the separate so far, and we will discuss it in the next slide. So for this part, we would like to discuss an instance of ETSP can actually induce to an instance of EPC by this treatment. Okay. I think your question will be answered by this slide. Okay, let's consider an optimal circle and a separator. We denote the separator by sigma. Okay, it is. We could observe that the optimal cycle could be divided by the separator into three parts. Okay, the first part is contain the passes in the separator. Okay, there are three passes, and the second part is contains the passes outside the separator. There are three passes, and the third part is the segment crossing the separator. We denote the segment crossing the separator by the origin lines. Okay. So let's focus on the passes inside the separator. Okay, we could observe that actually these passes is is the solution of a certain instance of EPC. Okay, let's recall the EPC. There are three inputs for the EPC. The first is the point of set, and the second input is a subset of the first input, and the third input is a perfect matrix on the second input. Okay, and for the first input, it could be identified by the separator. Okay, we identify each point in the separator into the point in P in. Okay, and for the second input, actually they are the end points of those segments crossing the separators. Okay, and for the third input, there are a certain perfect matching on the second input. That is the perfect matching on the boundary point inside the separator. So with this identification, we can create if we have an instance of EPC and a separator, we could create the subproblem inside and outside of the separator. Okay. So here we give a more formal definition on the identification of the subproblem. And I think we should just discuss the idea of this. Actually, we use the property of the solution to the instance of EPC. Each point in a boundary point should connect exact to one point in P, and for other points should exact connect to 2 points. Okay, and we use this property to identify the subproblems, to identify the boundary point in the subproblems. Also, I will skip the detail and discuss the merging procedures. Okay, once we have this is a divide and conquer algorithm. And if we would like to merge, once we have the solution to the subproblem inside and the subproblem outside of the separator, it may not so clear. Okay, so we could merge, we could union the solution of solution to the subproblem inside and outside of separator to obtain the solution to the larger problem. And okay, so of course some of the solution some of the solution cannot create the solution to the bigger problem, because we have to satisfy the solution to the larger problem have to satisfy the end point of the passes must be the points in the boundary points. Okay, for example, let's consider these 3 points. Okay, here we have a pass. Okay, that is defined by the passes outside the separator. But if we consider such a solution, it is a valid solution for the outside of the this is a valid solution to the subproblem outside of the separator. However, the union of these two solutions cannot obtain the solution to the the larger problem. Because it violates this property. Therefore, if we would like to if we would like to merge, or we would like to obtain all of the solution to this this problem, we would like to check all of the combination of the solution, one for inside and the other for outside of the separator. Okay, so let's give in instance of Euclidean path cover with input PBM, and we could divide the instance of EPC into 3 parts. Okay, and first we have to consider all of the possible connecting configuration. That is the set of points crossing the separator. Okay. Second, we would like to consider all of the combination of the solution inside and outside of the separator. And once we can do that, the optimal solution of the larger problem supposed to lies in our fully considerations. Okay, and later I will discuss the upper bound of the number of the connecting configuration and the upper bound of the solution, the combination of the solutions. Actually, these two consideration we will implement them by 2 for loop, and the time complexity of the divide and conquer algorithm is dominated by this 2 for loop. Okay, let's discuss the first part. Okay. Before we discuss the upper bound of the number of connecting configuration, we have to discuss some packing property. Okay, what is the packing property? We have the effect on the optimal circle of Euclidean traveling self-sustaining problem. The fact is that the set of segments in the optimal circle and the crossing a separator satisfy the packing property. And the idea of packing property is that there cannot be too many long segments crossing a separator. Okay, this is the basic idea. And if we formulate, we can formulate it by the packing property. Okay, so it is sufficient to consider those of connecting configuration, or we can say a set of segments satisfy this packing property. And this we can consider such a set of connecting configuration C sigma P, and C sigma P is actually a set of connecting configuration satisfying the packing property, and for each connecting configuration cross the separator sigma. Okay, so that is to say we do not have to consider each connecting between the point inside and outside of the separator, because for those segment with long length, we could ignore them. Okay, so okay, LS is the length of the segment. Okay, and we like to compare with the size of sigma, that is the size of the separator, that is defined by the length of the the edge of the separator.
Length of size is the
Yeah, the length of this edge.
oh,
Okay, yeah. So Chen actually use this packing property to design a separator theory. Okay, what is the separator theory? Given a set point P in d-dimensional Euclidean space and a subset Q that is belong to P, and we can find a delta balance separator respect to Q. That means we could use the separator to partition the set of Q evenly. Okay, and we could find the separator in polynomial time. And okay, and there are a lot of connecting configuration between the point inside and outside of the separator, right? And the separator theory give an upper bound on such the connecting configuration. Okay, for each connecting configuration contain at most C1 times n to the power of 1 minus 1 over d. Okay, so there cannot be too many segments crossing the separator. Okay, furthermore, the number of connecting configuration is also bounded by the separator theory. It is bounded by the sub-exponential number. Okay. Here we give an illustration on the connecting configuration. Okay, there are a lot of connecting configuration that could connect the point inside and the point outside of the separator. And we could label them by SII equal to 1 to the size of C, and we in the end we have to consider all of these possible connecting configurations. Okay, therefore, the separator theory gives us an upper bound for this consideration. That is to say, it gives an upper bound for the for loop in the divide and conquer algorithms.
what do you mean for those points set by the packing property, which is denoted by C sigma?
Yeah, the C sigma P is defined by those connecting configuration satisfies the packing property.
Meaning the summation of all the data crossing the conflict is smaller than the.
Oh, not the summation. Oh, you mean summation the number?
All the crossing.
Oh, actually, the packing property is that there cannot be too many long segments crossing a separator. That means, okay, there may be some segment crossing the separator, but there cannot be too many compared with the size of the instance. So it's supposed to in the big of 1. So, yeah. And the separator theory is we consider such a connecting configuration for all connecting configuration, and the separator theory bound the number of the connecting configuration. The number, yeah.
So you compare the length, not the boundary, the crossing length, not the cube length.
Okay, so let's define what is the long length. The define of the long length is the for those segment length larger than the length of the hypercube or the separator. That's the definition of the long length. Okay, so here we we could consider all of the possible connecting configuration, and we can bound the number by the separator theory so far. And next, we would like to bound all of the combination of the solution to subproblems, one for inside and the other for outside of the separator. Okay, so we would like to bound it by the reduced algorithm. Okay, that's given a set of points P in Euclidean space and a set of boundary points that is a subset of P. And we would like to bound how many EPC are possible for all perfect matching M on B. That means we are given P and the set of P and a set a subset and a subset B, and there are many choices for M, right? So we would like to consider all of the perfect matching M on the second input. If we just count the number of perfect matching directly, we would obtain this number, okay, 2 to the power of size of B times log of the size of B. And this is actually a large number. And the power of reduced algorithm is to reduce the number of perfect matching from this number to 2 to the power of B by this connectivity constraint. Okay, so what is the connectivity constraint? We could take this figure as an illustration. That's giving a set of paths outside sigma. We would like to so it's not so clear. Okay. 这边应该没有，不过没关系。I think that it's because there are some deformation for the output of the PDF file. Yeah. Is that get better?
Now we can see the dash line.
Okay. 因为这边可能会被截到。
Well, that maybe that is more like for this stage.
Okay. So let's consider given passes outside of a separator sigma. Okay, and actually this pass define a perfect matching N on the given point of set on the point of boundary points. Okay, and actually we would like to find for the passes inside the separator, we would like to find the perfect matching. Okay, that we denote by Mi. That is such that the union of M and the Mi form a Hamiltonian cycle. That means form a cycle. Okay, that actually for a given M, there are a lot of Mi, and actually we just have to keep the Mi with the minimum total length. There, that is to say, we could regard a lot of Mi. That would help the reduced algorithm to reduce the number of all perfect matching from this number to a smaller sub exponential number. Okay, now we would like to use the reduced algorithm to bound the we would like to use the reduced algorithm to bound the solution, the combination of the solution, one for inside and the other for outside of the separator. Okay, the reduced algorithm gives us that the number of possible solutions in or out of separator is bounded by the boundary points inside or outside of the separator. Okay, and therefore, if we would like to consider all combination of the solution to this subproblem, we have to use this time step. That is the this number times this number. And finally, if we would like to reduce this number, okay, we would like to find a delta balance the separator with respect to boundary points. And remember that we could use the separator to separate or to partition a set point into two parts efficiently. However, this separator cannot reduce the size of the problem efficiently. So here we will show how to find the solution to an instant of EPC by a divide and conquer algorithms. Okay, that's given instance of EPC. Okay, it could within a separator in that we denote the separator by sigma 0. And first, we create a separator. Okay, that could partition all of the points into two parts, and it will use polynomial time. And second, we should consider all of the possible connecting configurations. That means we have to consider all of the possible set of segments crossing the separators. And this number is actually could be bounded by the separator theory by the sub-exponential factor. And the third step is that we would like to identify the subproblem, one for inside and the other for outside of the separator. Okay. And it also takes polynomial time step. And assume once we have the solution to this subproblem, we should consider all of the combination of solution, one for inside and the other for outside of the separator, and then do the merging procedures. And consider all of the possible combination of perfect matching would take this time step. That is given by the reduced algorithm. And finally, the optimal solution of EPC must lie in our two considerations, and we could obtain the optimal solutions. Okay, so as we have discussed, there are two for loops. Okay, for the first for loop, we have to consider all of the connected configurations. Okay, that's we denote it by SI. That's in the set of connecting configurations. And once we identify the subproblem inside and outside of the separator, we will call the algorithm again, and we will discuss it later. And okay. And for the second for loop, we would like to merge the solution to the subproblem, and we do the merging procedure. And actually, the time complexity of the divide and conquer algorithm is actually dominated by these two for loop. And the first for loop is related to the number of points. And the second for loop is dominated by the number of boundary points. Okay, if we would like to reduce the time step of the first for loop, okay, we would like to reduce the points of the subproblem efficiently. That is to say, we need a delta balance separator, okay, with respect to all the points. Okay, this separator could reduce the size of problem efficiently, but it may add boundary point to its subproblem. Okay, and if we add too many boundary points to this subproblem, we will increase the time step needed to execute the second for loop. Therefore, we need another separator that is balanced to the boundary point. That means we could reduce the boundary point efficiently. Then we could reduce the time step of the second for loop efficiently. And our contribution is to determine the criteria to create these two kinds of separator. So let's start is by, okay, let's go through the fully divide and conquer algorithm. Okay, this algorithm gives the input of a point of set P and a subset B belong to P. Okay, this is the first and the second input of the instance of an instance of EPC, and the target of the algorithm to find the optimal solution of EPC PBM for all perfect match N on the boundary point. And we have discussed we need two separators to balance the time complexity. And our contribution is to give the criteria to compute these two separators. Okay. And once we have once we compute a separator, okay, this is the separator, and we have to consider all of the possible connecting configuration. Okay, that's the set of segment crossing the separator. Okay, so given a separator, we could divide the. Okay, we could create a lot of connecting configuration, and for each connecting configuration, we will create subproblem, one for inside and the other for outside of the separator, and we will recursive code this algorithm to create more subproblems that help to divide the large problem into multiple smaller problems. Okay, and once we have the solution to this subproblem, we should merge them. And this is the merging procedure we have discussed. That is to say, we have to check the we have to check if the solution inside and outside of the separator could be merged, and then merge them. Okay, so let's discuss the overall time complexity. Let's begin is by the first recursion. Let's discuss is by the first recursion. Okay, first we make a separator sigma 0 that could partition a set of points into two parts. Okay, then we use a recursive tree to discuss these problems. Then we will for this problem, we recursive code the algorithm to make more subproblem that help to reduce the size of subproblems. Okay, and we do it recursively, then until the size of subproblem is small enough that we could obtain the solutions of all. Until we could obtain all of the solutions. And actually, the overall time complexity is the summation over all of the nodes on the time complexity of the second for loop. Because for each node, we have to execute the second for loop. That means we have to do the merging procedure for each of the subproblems. Okay, if we can, so it's sufficient to upper bound the number of nodes and upper bound the time complexity of the second for loop to bound the overall time complexity. And our adaptive criterion could improve these two terms quadratically. Okay, let's first consider the time complexity of the second for loop. The reduced algorithm has actually given us that the iteration of the second for loop is in the big O is proportional to the power of the size of boundary points, and the size of boundary points is actually could be bounded by the criteria of creating the separator. That means the size of boundary points could be bounded by these criteria. Okay, why is that? Because if the size of boundary point is too large, then we will make a separator balance to boundary point, and that could reduce the size of boundary point efficiently. And our contribution is to modify the criteria. Okay, first we partition the size of the point into a set of intervals, and we use the label of the set of interval to define a gamma, a ratio that depends on the L, such that and we can verify that the gamma is larger than 2 times gamma L for all L. That means the boundary points could be reduced by a half by using our criteria. If we could reduce the size of the boundary point by a half, then we could improve the time complexity of the second for loop quadratically. Okay. Okay, we could partition a number of points into a set of interval, right? And the interval is defined by delta L and delta L plus 1 times n.
By all the points into L group.
Yeah.
All those boundary points.
Yeah.
Arbitrary.
You mean
divide that?
Okay, by you mean how to determine L?
Yes.
Okay. We have so we first we have to know the size of P, right? And once we know the size of P, then we could determine what is L is. Yeah. Okay. So let's discuss the second thing we would like to bound. We would like to bound the number of nodes. Okay, so first we use a separator to create multiple subproblems. And the number of subproblems is actually dominated. Is actually determined by the number of connecting configuration, and the number of connecting configuration is bounded by the separator theory, as we have discussed, and we could use the splitting procedure recursively, and we could obtain that the number of nodes in L's recursion could be bounded by knowing the upper bound of the number of points among previous recursions. Notice that NL is the upper bound of the number of points among the subproblem. That is to say, for the first recursion, okay, there are a lot of subproblems, and some we use N1 to upper bound all of the the number of points among all of these subproblems. So once we could upper bound this number for all k smaller than L, then we could upper bound NL. And our contribution is to derive that we could use our adaptive criterion to reduce NK quadratically. Therefore, we could reduce the number of nodes in the recursive tree quadratically. That is to say, we could improve the time complexity. Okay, so I would like to discuss two cases to describe the size of N and NK. Okay, let's consider a series of problems such that P1, B1 is a subproblem of P0, B0, and all of these subproblems are making a separator balance to its points. And we could use the definition of balanced operator to bound the size of PL by this inequality. Okay. However, if there are some separator is balanced to its bounded point, then we cannot have this inequality because we cannot reduce the size of point efficiently at last step. So in order to consider the worst case, okay, we would like to make a separator that's balanced to the boundary point successively, and we would like to ask how many recursive calls are needed to reduce the size of the subproblem by ratio of delta. Okay. Okay, let's discuss our modification first. Okay, if we make a separator balance to its boundary point, and our criterion will enforce the separator will the next separator is supposed to be a separator balance to its boundary balance to all of these points. That is, we have to make a separator balance to P. That means we just need two recursive calls to reduce the size of problem by ratio of delta. Okay. However, in the previous work from the Berg, they need 4 recursive calls to reduce the size of the size of subproblems. So therefore, our contribution could be obtained by these illustrations. So let's discuss the conclusion. First, we could solve an instance of ETSP by a divide and conquer algorithm, and the time complexity could be dominated by 2 for loops. And there are two separators to reduce the time step of this for loop. And our contribution is to optimize the criterion to create this separator. And we obtain a quadratic speedup compared with the previous algorithm. Okay. This is the end of my talk. Any questions?
Basically, designing a better strategy and use self-IO, and then
yes,
can efficiently use the
yes, yeah. Because our criterion could reduce the upper bound of the boundary points. That improves the time complexity of the merging procedure. And also we could make a more efficient way to reduce the size of the problem. Yeah, so therefore we do not so many time steps to reduce the size of the problem. Yeah.
So that basically depends on all the formula you show. So it's just create a table for all different functions.
Yeah. Yeah. Delta is actually a constant. Yeah. So any integer could be divided by the set of interval, right?
But delta is defined below.
Okay. Yeah. So first we define, we identify what is L. Then we use this equation to define what is gamma L, and use this to decide what kind of separator we would like to create. C1, you mean? Oh, C1 is actually the constant we discussed in the separator theory. That is a constant that is the independence on the size of the problem. Is there a question?不用。干嘛？要看有没有那个吗
？Is there any question or comment from the audience? Okay, if not, let's thank Dr. Chen Kuo-Chin today for the talk. Thank you.
Thank you. 一开始我那个连线有问题，就我电脑连不进去，所以那有花时